reason we make our powers chart is so that we can solve some exponential equations without the use of our calculator. So first of all, top of the next page, we can highlight what is an exponential equation. That is where x is in the exponent. And what we're going to do right now is we're going to look at questions like 3 to the x is equal to 81. You might be able to do it in your head, but what we're going to use as a technique is we're going to go back to our powers chart and see if the base is 3, does 81 ever show up as a power? Yes, it does. 81 is 3 to the exponent of 4. So we can replace the 81 with a 3 to the exponent of 4, and then just by observation and be like, oh, if 3 to the x equals 3 to the 4, then x has to be 4. So if we can get the bases the same on both sides, then you'll be able to solve for the exponent. Right? It is not hard if I tell you this. What is x? If I have 2 to the x equals 2 to the 7, can you see like, oh, this is pretty easy. If they're going to be equal, x would have to be 7. You don't need to know what 2 to the, you don't need to know 2 to the 7 is 128 to figure this out. If it's in this form, we're going to be able to solve for things because the exponents have to be equal. Getting it to this form is going to use all of our exponent laws from grade 9 and revisit them. So if we go to example 1, in part A, we have 4 to the x equals 1 over 256. And the question will be, if I go to my powers chart, is 256 in my powers of 4? So we scroll back up to our powers chart. There's my powers of 4. Sure enough, 4 to the exponent of 4 is 256. So I can go back to this question, and I can now write 4 to the x is equal to 1 over 4 to the 4. And if we have a power in our denominator, we have a rule that says if you want to, you could bring that to your numerator with your negative exponent rule. That having that 4 to the 4 on the bottom is like having 4 to the negative 4. And this is our goal. We've used our exponent laws to get both sides as a power of 4. And at this point, I like to do this. I like to take out different colors, circle that, and go, so, because it's not really a mathematical thing that we're doing right now. This is like, by observation, x has to equal negative 4. Because right now, you have no technique for getting that x out of the exponent. We're going to learn a technique this year. We're going to learn how to use logarithms. But at this moment, all we can do is go, those things have to be the same. The only way it makes sense that 4 to something equals 4 to something else if those two somethings were the same. And so we had to use our exponent laws to switch things around to change 256 to get it to 4 to the negative 4. In part B, we have 27x equals 9 to the 2x minus 1. So if we went to our powers chart, you might first go to your powers chart and look at powers of 9 and be like, oh, but I don't have 27 there. And I definitely don't even have 27 on my powers chart. So the next level is to see, do 27 and 9 happen in the same column for a different base? And sure enough, if we're looking at our base of 3, 3 cubed is 27, 3 squared is 9. So our goal in this question is to get things to have the same base. And I can do that by changing 27 to a base of 3. So I change the 27 to 3 cubed, there'd still be an x outside. I change the 9 to a base of 3, and there would still be the 2x minus 1. So our first goal is to try to get everything in the same base. We did that in part A, getting everything in the base of 4. And then we have to use our exponent rules so we get just a single power on both sides equal to each other. So now what is your exponent rule for a power to a power? Do you add, do you multiply, do you guess? Right? Power to a power, you're going to multiply. Sometimes, if you forget an exponent rule, the best strategy is just use simple numbers and think about, what does this mean? Right? An exponent means repeated multiplication. So if I have 3 squared cubed, does this make sense that this is 3 squared 3 times? And each of those squareds would be like, I think at this point you would have figured it out, but, oh, I have 6 of them. What's the shortcut? Instead of going through all of this, would be to multiply. But if I've forgotten an exponent rule, I can go back to an easier set of numbers, and it doesn't take very long to figure it out. So here I need to multiply. This will be 3 to the 3x, and here I'm going to need to multiply. And when I multiply this, it's going to be 4x minus 2. I'm going to have to distribute. And now we've succeeded on getting a single power on both sides with the same base. I can go to this next very mathematical step where I go, so 3x has to equal 4x minus 2. And this is an easy equation to solve. I can move my x's over to this side, move my 2 over to this side, combine my like terms, and I get that x has to be 2 for this to work out. So the strategy is, if you can get a single power on both sides with the same base, then the exponents have to be equal to each other. Questions to circle, 3, 4, 5,